beginning of the next slot. If a station can send the data at this point, if it has a data to send at this point, it should not send at this point. Instead, it has to wait for this long. So then it can send the next beginning of the next slot. Okay. So this is what the mandatory things we made in slotted ALOHA. So the modified of that. So what we call it as slotted ALOHA protocol. Okay. So the rest, whatever we saw, the same thing. The backup timer, the binary exponential algorithm would be the same. But what was the vulnerability time here in slotted ALOHA? Okay, the vulnerability time is means that finding out in which slot the frame may get involved in collision. Okay, if you would see here in this example, we would see slot 2 and slot 3 where frame is involved in collision, isn't it? If you see here in slot 2 and slot 3, the frame is some frames for get involved collision. This is due to of why? Due to of what reason? There might be more than one station if they were transmitting the data at the same slot. Okay, so I'm not said that in one slot each slot would be reserved for each station. It is not like that. So we made a channels to be accessed in slot, but anybody can access the channel at any slot. Okay, so the reason of collision here is if in a one slot, if a more than a one station, if they were transmitting the data, then that leads to have the collision. See here in this slot, station 2 and station 3 was transmitting their data. Okay, and in this slot, station 1 and station 4 were transmitting their data, isn't it? So this, if this situation comes, then the frames are or collide. Okay, in one slot, if more than one station, if they are transmitting their data, then that leads to have the collision. So then what is the vulnerable time now? V of t or v time, vulnerable time, or t vulnerable, I would call that. I'll call that t vulnerable equals how much in during which slots they are involved in collision in 1 tt. Okay, so or I can also write them as 1 tfr. Isn't it? The vulnerability time of this protocol is during this time tt, in 1 tt, the slot is actually made up of with 1 tt. So you can see this was the transmission time of the frame, right? Because so it depends on length by b. So this slot is created in such a way where it exactly is equals to the transmission time of the each station to transmit their own frames. Okay, so then I would say the vulnerability time, the time the frames are involved in collision is 180 if more than one station were transmitting in the same slot. Okay, what if so? If I would see this example, uh, I said an assumption we made in initially there were 4 stations and each stations would be having exactly 2 frames to send. So how many frames were sent by all of them? 8 frames, because 2 from each one, 4 stations, totally 8 frames. Out of frame 8, by using the slotted ALOHA, if I see this example, how many frames were survived or were completely transmitted? This one, this one, this one, and this one. So out of 8 frames, 4 frames were successfully complete their transmission. So another 4 frames were there involved in collision. See this two and this two. Okay, I would say I can increase something a 50% of efficiency than what we were able to achieve in pure ALOHA. Pure ALOHA, if you see that example, out of 8, I would say only 2 frames were successfully completed or survived. Then remaining 6 frames were collided. So 6 frames were lost. Okay. isn't it? So after you made this modifications, we like started ALOHA, so we were able to increase somewhat, we were able to increase the efficiency of this protocol. Okay, so we will now see what is the efficiency formula and how we will calculate that. Okay, okay. If I go further, to see what was the efficiency formula here, only the same formula, but in ALOHA, it is e to the power of minus 2g, right? This 2 comes from the vulnerability time for of that ALOHA, pure ALOHA is 280, right? So this actually 2 comes from there. But here we in vulnerability time become 180, so that your expression will become S equals to G into e to the power of minus. And what that G represents here, the G is equal to what? The average of average frames that is generated by a system. The average frame that is generated by a system in 1T. System in 180. So that is what G is here. Okay. So in started if I see this diagram, so when frames will not collision free in one part, it only one collision would send exactly one frame, then that frames will be survived or it will not be involved in collision. What will be becomes here? Average number of frames are transmitted in one time slot. One time slot, I would say it is 180, right? Then if you'll get a maximum efficiency when G will becomes equal to 1. When G is equals to 1, you get the maximum efficiency. And if you substitute here G is equal to 1, 1 into e to the power of minus 1. And if you solve this, you'll get 0.368. 0.368, and that is the efficiency or the maximum throughput of this protocol. So what is the maximum throughput? That is 6.8. So quite double the what we were able to get
Your
in the
voice
pure
break
ALOHA.
ಆಗ್ತಿದೆ
Pure
sir.
ALOHA. Okay. Now it's audible.
Yes sir.
Okay. Okay. So in pure ALOHA, so we were only able to get 18.4 something, but by making this modifications, we are now able to get the efficiency which is doubles the pure ALOHA, which is 36.8%. Okay. So then let me do some problems on this. Problems is something what we would just did in the previous one. So this is what the vulnerability time of the slotted ALOHA. Vulnerability time is nothing but the time period that the frames are involved in collision is 1 TFR, or I would say it is 180. If more than a one station, if they would send the frame in the same time slot, then that frames were uh, involved in collision. Okay, so that is what the vulnerability time. So then same thing we will do the problems what we did in the pure ALOHA. If you take a slotted ALOHA network, okay, and the transmission they given the length of that frame, okay, and they were given the bandwidth, so they are asking us to find out what was the throughput if the systems were produced 1000 frames per second, 500 frames per second, and 250 frames per second. So we know that how to find the tt. So tt is equals to l by b. So what is l now? L is here 200 bits, so that, and kb becomes 2200 kb per second. So then you will get the TT as 1 millisecond, isn't it? So you find out what is called TT. So then they were asking us to find out what was the throughput. Throughput we know that it is S into e to the power g into e to the power of minus g, isn't it? So S is becomes now g into e to the power of minus g, right? So we have to find. So if a frame, if a station can generate 1000 frames per second, how many frames that would be generated in 1 TT? So in 1 millisecond, how many frames were generated? If a station would generate a frames of thousands per second, so then in 1 TT, a station can only generate one frame, isn't it? Then the G will becomes what? 1. So if you substitute this 1 here in this expression, you will get the efficiency is 36.8%. So then how you will find out the throughput? Throughput is something, it is N into efficiency into bandwidth, sorry, N into what is called this one, uh, number of frames that we generated. So that is 0.0368 into 1000. So you will get 368 frames for completed their transmission. Out of 1000 frames, so 368 frames were completed their transmission. Okay. Similarly, if I go with next one, if a station would transmit at 500 frames, or if they are generated 500 frames per second, and what was the efficiency in slotted ALOHA? So we have to find the G now. G is, if a station would generate 500 frames per second, what was the frames it is generated per 1 TT? So it is half a frame. Okay. So then if you substitute G is equals to 1 by 2 in this expression, you would get 30.3% as the uh, efficiency, okay, or throughput. So throughput will becomes 5 into 500 into 0.0303, then you'll get 151 frames for completed their transmission out of 500 frames. Or similarly, if a station would transmit generates 250 frames per second, find out G, then G will becomes 1 by 4. Substitute this 1 by 4 in this expression, you will get 19.5 as the percent successful or survivor rate is 19.5. And if you multiply this with the total number of frames that been transmitted or generated by a station, you will get the 49 frames were completed their transmission on this shared channel by using this slotted ALOHA. So we were able to get rate, or I would say that there will be no collision more in slotted ALOHA as you compare with pure ALOHA. Okay, is that clear? Is that clear? Yes, no, maybe.
Yes, sir.
Okay.
Yes, sir.
Shall I go to the next one? Okay. The next one. Okay. So what after we were seeing this ALOHA, so we will still lag with the efficiency. See, actually at least I get more than 50%. But what was the maximum efficiency I would get in pure ALOHA? Sorry, in slotted ALOHA is 36%. So we were trying to enhance rate, means we have to trying to decrease the collision, because if you don't have that success rate high, that if the packets were being collide, then your network will not is not effective. Not effective means, so the retransmission of the frames would be high, and efficiency of your network, because as you've been sending and the frames were being collide, so and again you're retransmitting the same frames, probably it may degrade your network performance, right? So we should at least nearly have much efficiency or the success rate where your frame should not be collide. So in that case, I would say your network performance would also increase as you decrease the number of collision in your broadcast link by using any of this uh, multiple access method. Okay, the next one is what we were discussing here is CSMA. Okay, So it would also the similar what we just saw, could be an aloha or it could be a slotted aloha. So one thing we just added to this is carrier sense. Okay. So what you mean by that? It is like a listen before you talk. Okay. So what we saw there in a slotted aloha or a pure aloha, there will be no none of the station will use this function, right? The function is something before you send, you look if the channel is idle, then you can send. If you found the channel is busy, then you should not send at that time. We wait for next lot to send. Okay, if you would add this to there in slotted aloha, probably you might be getting collision free. Means you will get completely 100% so the efficiency, so that if you would send 1,000 frames generated by a station, all the frames were successfully transmitted. There will be no collision at all. Okay. So, but what we made the next thing here, carrier sense multiple access. This was the one of the protocol which majorly used in today's network. Okay. So carrier sense multiple access is just a concept of concept theory concept, but the practically implemented protocols were these two: CSMA bar CD, CSMA bar CD, and another one is CSMA bar CA. Okay, so this was the two multiple access method we were using today, and this CSMA bar CD we are using in wired LAN, and the CSMA bar CA we were using in wireless LAN. So why it is not used? Why CSMA bar CD is not used in wireless? I'll just explain you that, and I'll also give the reason why it is not used. So why it is used in CSMA bar CD in wired, and also I'll explain you that what actually it means. So as you would sending a data in a common channel, the station simultaneously would also listen for is there any collision. So that is what you mean by CSMA bar CD. As you would sending a data, simultaneously it would also listen for collision. If there is some collision signal come back to that station, it will detect and it will retransmit the data. In CSMA bar CD, there will be no acknowledgement mechanism. So since the each station will have a features that as it send the data, simultaneously it would also listen for collision. If it receives the collide signals, then it will detect the collision. Means it would comes to know its own data is involved in collision, so that the same data will be retransmitted again after following this procedure what we defined in this carrier sense multiple access. Okay, but in here in wireless we were not able to detect the collision because since the channel will be more attenuated, so the power at which the signal that you would send. Okay, so you might be having different power levels for a normal transmission of data, and for the collide signal you might be getting a double the power signal after they are overlapped. So since if you would send a collide signal on the air medium, so this may get frequency may get attenuated due to this of that medium. Since hence this may since it get attenuated, so where at the receiver, so it cannot be distinguished whether it actually a normal signal, the data which is normal data, or it might be collide data. Since due to this nature, where so here in a broadcast like in a wireless network, so we were not able to detect the collision. So that's why we were having some strategies to to avoid the collision. So that's why we call this protocol as collision avoidance. So this was used in wireless and this was used in wired network. We will discuss that later. Before that, let us understand. So what is this? So what is the CSMA? Okay. 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 Let us consider this diagram. So there were four stations A, B, C, D, and all of these four stations was connected to common channel. Okay. So what we were added here in this protocol is sense the carrier before you send. Sense the carrier before you send. If the channel is carrier is free, then a station can send the data. If the channel is busy, then it should not send. So that is the simple thing we just added to this multiple access method to to avoid the probability of collision, or avoid the collision what we were able to get in the previous protocols. Okay, but we would still have a collision after we adding this feature to this multiple access method. What was the features? So let us assume, let us there is a one broadcast room, like room I would call them as one broadcast domain. There were so many people who were there. Okay, so we said anyone can talk at any time. Okay, so in the pure aloha or slotted aloha, what we would assume, so there is one broadcast domain. I said them any can talk at any time. So if they would like to talk. Okay, due to this pure aloha, what I said, so they can start talking. Probably if the same time if more than one they would talk, there will be collision, isn't it? There will be collision. Okay, so that should we are trying to avoid, right? So what we said them, so before you start talking, you listen. If someone will talk, then should not talk. If nobody will talk, then you can talk. So in aloha what we made, it is they can talk even someone would already is talking. So that due to that we were able to get more collision. But in carrier sense multiple access, we set them, we instruct them, each one of them, before you talking, you listen. If someone was talking, then you should not talk. Once they finish, then you can talk. So that is what we just made here in this multiple access method. Okay, probably by having this uh, and start. If someone would start talking, the other will also listen. If he stops, then he can start. So then there will be no collision at all. Okay, but there is a collision still would exist in CSMA, and that is what we should find out the vulnerability time. So in order to understand that, this was the diagram. The space-time model would be written, or I am explaining to understand when that collision would takes place. Okay, the collision is takes place. Let us take all of them were connected. So this B would start sending the frame at time t1, and C would start at time t2. So at this time, okay, the B station will sense the channel, and no one else is sending it their data. So then they can start. So it would comes to know I can start because the channel is idle, so I can start the data. Okay, as you started, okay, so this bit what you send, it would take some time to reach at the all station, right? Because due to this propagation delay, so what after you sending by station B, it will take some time to reach station C and station D, because that is involved with the propagation delay TP, isn't it? So before the reaching of that data at the station C, if at time t2, before that, if station C would sense the channel, what it would comes to know, it would comes to know the channel is the free, so that it could also start transmitting the data, isn't it? So is what, if you see this, assume this would be a road. Okay, standing at this point, if I stand at here and this is a road, can I able to say whether this road is completely free or not? So I can't say that whether the road is free or someone vehicles is moving. I could only tell at this, seeing at this this point, at seeing at this point whether this road is free or not. I will means turning like this, turning like this. I would able to say, but how the station will turn and see whether this link is free or not? It could only check at where point, the point at which the host is connected. Standing here, I could only say by seeing at this means in sight how many like vision I have. By seeing this vision, I would say if any vehicles were traveling in this site, I would say the road is busy. If none of the vehicles is traveling, then I would say the road is free. The station would also sense where the channel, the host was connected to the channel. At that point, it only check is any of this energy would be present in that point. So then it would comes to know it would be busy. So if none of the transmission is happened, then the channel becomes idle. So then it would comes to know it is free. So that is what you mean by carrier sensing. Okay. So before this frame, the signal will reach the station C. Before that, if station A C will sense the channel, then it would comes to know it is free. Then it will also transmit their data. At this point, okay, is actually what it is involved in collision. Okay, so this is the area where the B signal is exist, and this is the area both the signals were collide each other. This is the area where both the signals of stations B and the station A, station B and C and are involved in collision. This is the area of the signal where this B is transmitted to the station A, and this is the area where the signal C is transmitted to station D. So what we would understand here, so there will be still the existing of collision due to this vulnerability time. So sorry, the vulnerability time is what? The propagation delay. Because as the station would transmit, it would take some time to reach that signal will be heard by everyone. So means what? What was the previous example I just took? In this room, I said them to listen before you talk. So there might be a chance the another person would also start. If someone would start where what is talking would not be heard by the another person. So then he might think if nobody will be talking so that I can start. Isn't it? Due to this propagation delay, so there will be still a proper like, collision in your CSMA. Okay, that is what this diagram says. At this point, if the C would B will sense the channel and it will comes to know it is idle, then it will transmit. So at this time, if C would sense, then it would comes to know channel is busy because B would be transmitting. Again, D, if it sends at this point, it will be also in reframe or it should not send the data because B would be utilizing this channel. So before that, if C would sense at this point or D would also sense at this point, both will be comes to know the channel will be free because still these signals will not reach, that will not be heard by station C and station D. Okay, so that is due to this vulnerability time of the propagation delay. There will be still existing of the collision in the CSMA protocol. Okay, if you would not have this propagation delay, as this B would send and immediately that signal will be heard by both station A and both station D and station C. So there will be no collision at all. I could say you could use CSMA where you will get the successful rate of 100%. So there might be still exist due to of this propagation delay. Okay, so this is the one thing. So we would say that so we were adding a carrier sense before you send. Okay, so what should each host should behave? How each host should behave if they found a carrier is free? Okay, carrier is idle and what the station should do if the carrier is busy. Okay, so in order to tell the behavior of the each host, how they should behave in this idle, when the channel is idle and when the channel is busy. So for that we were having three methods. We call them as persistence method. So the behavior of three persistence method of an host, how they should behave whenever the channel is busy and the channel is idle. Okay, we call this as one persistence, non-persistence, and a pre-persistence, probability persistence. Pre-persistence means probability persistence. Okay, so in order to explain this, let me explain them in the time diagram. I'll just representing the channel in terms of time. Okay, and I am assuming this duration of time the channel was utilizing for carrying of some host, some other host data. Okay, assuming this will be a shared channel, and during this time I'm assuming the channel might be carrying of some other host data, and that will be represented as busy, because since someone would be transmitting, the channel is obviously is busy, right? So in that time, where if the other host connected to the same channel, they should continuously sense the channel. Okay, so continuously sense. Once the channel is becomes idle, then you can immediately you can transmit. So this analogous is how it likes means, when you are trying to call your friend and your friend is talking with someone, uh, how you should behave. You should not keep continuously calling him, because even if you keep calling him, you'll get the same busy tone itself, right? So you should wait. What you will do, you will leave it. You will wait for 15 minutes. Then again you will call. After, again if you get busy, then again you will random time will wait and again you will call. Okay, but if this method in one persistence, if you would keep on continuously calling, obviously you will get busy tone itself. So that when you will do this thing, whenever you have an emergency, you should immediately talk to him. Then only will do this type of method, isn't it? You continuously call, and that person who comes to know there might be some emergency. That's why he is calling continuously. Then you will cut the call and he will take your call and he will talk. Okay, so that might be in real time, but here it is not like that. It continuously sends. Once it gets the channel becomes idle, then it will immediately send. So this method might utilize the channel completely, but what was the problem here? If you would use this method, persistence method, so there might be of more collision. So I taken one, probably might be continuously sends in the broadcast environment. Probably more than a station, one station means more stations would do the same thing. Means every one station, if they have data to send in a one common channel, they will completely sense the channel. All will be simultaneously get busy because someone would be transmitting. Once the channel is idle, all the hosts will get the channel is idle, then all of them will transmit at the same time. So then obviously there will be collision, right? So this is what the one persistence method. So but you could use, it depends on you. So what this one persistence said, so you continuously, this the flow chart will continuously check. You check the channel. If they're busy, if they're busy, it will go back again. You sense again. This what the sense. If channel is busy, if this busy, then you continuously sense. If that is free or idle, okay, or idle, then you send the fail. Then you send a fail. That is what this persistence method who tells us how this host should behave when the channel is busy and when channel is free. When channel is free, you send. Busy, you sense. That is what this method would tell us. Okay. The another one is the what I just said. Same scenario. We assuming this duration might be used by some other host for their transmission. Okay. how a host should behave here. You sense at some point, at some time. You call to your friend at some time. If you would comes to know they were busy, is busy, you wait some time, random time. Then again you sense. Again after sometimes again you'll call. After 1 minute, 2 minutes, again you'll call. Again that time you will find get a busy. Again you wait. You increase the random time, waiting time, and again you sense. See, the duration of this is less as you would check with this, because after you waiting 3 minutes, you would again getting busy. So probably you should understand. Probably your friend might be in a long conservation, long conservation. Okay, so then your waiting should time should be increased. Okay, then you will wait for next 5 minutes. Then again you will sense, you'll call. By the time you'll, if you found the channel is idle, if you get connect, then you can talk. Then you can start your conservation. So what here is something you sense the channel. I check the channel. If it is busy, if they're busy, so you wait for random, wait for time, wait for some time, and again you sense. If they were idle, if there is idle, then you immediately send it. So this was the flowchart. Check the channel. If they're busy, you wait for some random time. Again you sense and you check again. If it is busy, again you wait a random time and you check again. If it's idle, then you can send. Okay, that is what non-persistence method. Okay, you are not being persistently or continuously sensing. Instead, okay, on discrete time, I would be sensing the channel. Okay, at point zero, if I sense, next I will sense at some other time. Okay, so by using this method, non-persistence method, so probably the collision might be less compared with one persistence, right? So if all of, so all the stations, if they sense, if all of them are comes to know the channel is busy, so everyone will waiting for some random time. So that random times makes unlikely common for all the stations, isn't it? Okay, so again it will sense at different times. Probably all of them again, if they get busy, again they will increase the random time and they will wait. So that random, the waiting of this time slot makes to reduce the collision, right? But what was the disadvantage here? Due to this random waiting time, we may not be knowing during that waiting time the channel may get the chance been to idle. Okay, the efficiency of utilization of the link will be reduced, right? See here in this diagram, as still this duration, okay, the channel will be idle, but all the stations were waiting. So due to this persistence method, isn't it? They were waiting, and again at some point they will again sense. Because, but here before that itself the channel already been idle, right? So that we were not knowing it. Okay, the efficiency will be reduced, but the collision will be less. But here the collision will be more, and the efficiency of utilizing of the link will be more. Okay, hybriding these two is what we call as probability persistence. So we were adding both these two things. So what this means, same scenario we have taken, the channel will be busy during this time of transmission of some other station's data. The station should continuously sense the channel. Once they would comes to know the channel is idle, they should follow some time slot with the probability of some outcome where the station should wait for this random time slot. After that completing their time change, they should sense the channel. If they would comes to know the channel is free, then they can transmit the data. Okay, so that is what probability persistence. Okay, so let me show you the flow chart. Okay, this what the flow chart. The channel, if they are continuously sense, If they're busy, you check continuously. If they are idle, then you can transmit. For the non-persistence, the channel continuously check. If they're busy, wait randomly. Again, you sense. If they becomes idle, then you can transmit the data. In probability persistence, continuously check. If they're busy, continuously check. If they're idle, with the probability of outcome, if it is less than the probability P, then wait for time slot. Again, you check. Again, you check. If it is idle, again you comes here. If that is greater than the probability of P, then you can transmit. Or else, if they're busy, use this back off algorithm if they have occurred with any of this collision. So that is what P persistence would tell. Okay. So we might be using any of this persistence method, that depends on you. I would not say either we use a one persistence or P persistence or a P N persistence. In most of the time, we probably used to use the P persistence, since that would be an hybrid of these two. It would have a both advantages as well as the disadvantages. Okay, because here we would say so it would having both advantages and disadvantages of what we just looked at this two persistence method. Okay, so this is actually you to tell. So to understand what is called the collision detection. So this is all about CSMA. Now we were discussing about CSMA bar CD. So CSMA artha agide. So now we would just try to understand how a station will detect the collision. Okay, that is what together we call them as CSMA bar CD. Okay, so we understood carriers and multiple access. The station should sense the carrier before they would transmit. Okay, and how the station should behave after they would comes to know the station is free and the station is busy by using this three persistence method. Okay, so adding to that, how a station is as they are transmitting, how they would also listen for collision. Okay, so for that we were just having one scenario here, the diagram. So who tells that the station can identify its own data is involved in collision. Okay, let's take some examples and we'll try to understand. So let's take two stations. There were two stations, station A and station B. And are you able to see what I'm writing on this slide? Can anyone tell? Are
Yes,
you
sir.
able to see what I'm writing on this? Okay, so there were two stations. Okay, let me erase this slide and write it on this slide itself. Okay, instead of taking this four, let me take because I could only take two. Let us take station A and station B were there. Okay, station A and station B were there. Okay, and both the station they have the data to send. Okay, and they were sending their data on this channel. And station A would also send, station B would also send. Okay, let us consider the propagation delay from here A to B is 1 hour. Okay, at time at 10 o'clock, both at the time 10 o'clock, both the station will transmitted their data. Okay, at time exactly at 10:30, what will happen? The station A data will reach half of its length of the channel, and both the station B would also the signal will reach half of its length. At exactly at 10:30, there will be a collision between the stations A's data and stations B data. Okay, at what time the station A will comes to know will hear the collide signal? At exactly at 11, both the station, because as they are collide in half of its length, so it will takes an half an hour to come back the collide signals to the station A, and again the collide signal will also takes half an hour to reach the station B, because since they were the collision will happen at half of its way, again it would takes half the same propagation delay to reach the collide signal both to the station A and the station B. At exactly at 11, both the station would hears the collide signal. Means it will receive the collide signal. How this station A and station B would comes to know its own data is involved in collision. That is what the question mark here. how the station A and station B would come to know its own data is involved in collision. Because if you take in this example, if station A and station B are transmitting the data, probably station B and station C would also send their data. So probably that data may collide and that signal would be sent to station D and station A. That would also possible, right? Okay, how a station would comes to know its own data is involved in collision, how station D would comes to know its own data. Might be some other data might collide and that collide signal would be received by station A and station B. Isn't it? That would also possible, right? Isn't it? Okay. So the answer is this. It's very simple. Okay. As you take the same example, okay, the station A is sending, station B would also sending. Okay, at exactly some time, both this data would be sent. This data would also be sent, and this again at this point the collision will happen, and the collide signal would come back at some time, and again here also collide signal will come back at some time. The station when it is receiving the collide signal, if still it has some data to transmit, so in that time, so the station A would comes to know its own data is involved in collision. Okay, means that what in this carrier sense multiple access collision detection, when you are sending a data, you should send a data with some specific size so that a station would comes to know whether its own data is involved in collision when it has some still have some data to transmit. Okay, when the station has still this data to transmit, before that itself if they get back the collide signal, then that data then the station will confirm that its own data is involved in collision. Okay, so collision detection is actually how we were doing it. We were sending a data with some minimum length. So during still the station would transmitting some data. If they would get back the collide signal before that, then it would comes to know that it will ensures that its own data involved in collision. If it doesn't have any data to transmit, if after they would get the collide signal, then it will not make sure that its own data is involved in collision. Okay, so then what should be your L becomes in the CSMA bar CD. So this would be an ideal case. What if a station A would transmit at 10 and at exactly station B would transmit at 10:59. Okay, let's take an example that this was the scenario. Station A and station B were transmitting, and one hour is the propagation delay. Station A is transmitting at 10 o'clock. Okay, okay, 10 o'clock, and it will reach at exactly almost nearer to B. What if station B would transmit at 10:59? 10:59, almost near to the station B, there will be collision, and soon the collide signal will be reached by station B because that is immediately is next to it itself, right? But the collide signals to come back here by station A is almost 1 hour again. From 1 hour, it's from here to there. From there to again the collide signal comes back to station B A. It's again 1 hour. As it gets that time, your still A should have some more data to transmit, right? Means what? Your TT should be the transmission time should be greater than or equals to twice the propagation delay. Isn't it? Twice the propagation delay. Why I am taking 1 TP should be the data to travel almost at the another side, and another TP is the collide signal to come back to the station A. Station A, in that time, still if the station have a some more data to transmit, then it would comes to know its own data is involved in collision. How that would comes to know? It is TT. So we know that. So this is an expression. Your TT should be greater than the twice the propagation delay. And what is an expression for TT? It is L by B. L by B should be greater than twice the propagation delay. So then L becomes should be greater than equals to 2 TP into bandwidth. 2 TP into bandwidth. This was the expression. What was the minimum? The bits of data you need in CSMA bar CD network to detect the collision is it should be greater than twice the propagation delay into bandwidth. Okay, let us take an example that I have the propagation delay will be 6 microseconds, 6 microseconds, and I have the bandwidth of okay 10 Mbps. I have the bandwidth of 10 Mbps. What was the minimum size of the packet in order to detect the collision in the CSMA bar CD network? Okay, substitute that expression here. So L should be greater than or equals to 2 into TP. TP is what? 6 microsecond into 10 MB. 10 MB, right? So what you will get if you substitute here, this will get cancelled 60 into 2 becomes 120 bits. You just find out it how much. So this mega micro will cancel, right? 6 into 10 you will get 60 into 2 120 bits. If you convert the bits into bytes, divide it by 8, that will becomes that will becomes bytes in bytes. So that was the minimum size of the data you need in order to detect the collision. A simple understanding. Okay. So let me clear and erase this. Or this in diagram you can see at time t1 if A would transmitting the data, okay, and at time t2 if B would transmit, okay, B would transmit. At some point there will be collision, and that collision signal will come back at time t4. For C it will come at here at time t3. If still have data to transmit, then they will comes to know its own data is involved in collision. So that is what the transmission time I just said here. So that is what I have explained here. The same thing would be you should understand from this. Okay. So the next one you can see here that is what they written. So the polite signal should come back to the station A at that time. If this still station is transmitting, then it will detect the collision. Then it will abort the transmission of the data. Here also the same thing, and this was the transmission time of the station C before after the transmitting and the collide signal will be received. Okay. Okay. There is a simple example here. In a CSMA bar CD network, a bandwidth is 10 Mbps and the maximum propagation time is the TP is becomes 25.6 microseconds. What is the minimum size of the frame you need in CSMA bar CD? So they given the TP and we know that L should be greater than, you substitute that value 2 TP into bandwidth. So TP is given 2 into how much? TP. TP is 25.6. You'll get 51.6. This into bandwidth, you will get the 512 bits. 512 bits. If you convert that to bandwidth, sorry, bytes, you'll get 64 bytes is the minimum frames that I need in standard Ethernet in wired network. In LAN, wired LAN, we need in order to detect the collision. Okay, I'll explain you about this diagram that completely explain about your carrier sense multiple access with the collision detection. So, and this mantra we use for every protocol. What is that? We'll initialize this variable as 0. Okay, we initialize the variable for 0, and I will try to attempt for some attempts for 15 attempts. After this 15 attempts, if I'm trying and if I'm sending the frame and if all of the frames were involved in collision, I will abort this session and I will try that in some other time. That is what this K I used in every algorithm. Okay, I'll initialize that variables to 0 and I use any of this persistence method. Right. I sense the channel and I should behave in such a way how a host should, either it should send immediately, I should random wait for some slot, or I should use pre-persistence method. After that, if either I might be completed with my transmission or I should detect the collision. I should come to know whether I transmitted completely or collision is detected. If there is no, if there is no collision, I can transmit and I can receive, and this could continuously happen for every condition which I check. If they are eligible for transmission, then I will transmit, then I will receive the data. If it is yes, so I am not eligible for the transmission, then I will continuously check the collision which I have detected. If they are detected, then I'll send the jamming signal. Jamming signal ಅಂತಂದ್ರೆ in the broadcast channel, when I'm using this CSMA bus CD, is this station would comes to know the its own data is involved in collision. The station will send jamming signals to every other station, telling that you should not send this time so that I will completed my retransmission. That is what the sending of jamming signal means of. Okay, if no, then it will successful. Then I will increment the k value and I'll check with how many times I am read, how many attempts that I made. If if it is greater than 50, then I will abort this session. If not, then I will use this binary exponential algorithm of algorithm. After it, choosing it again, I will go with persistence method and I will repeat this same thing again and again. So this is what about the collision detection method. Is it clear? So then we'll try to derive an expression finding out the efficiency of this protocol, CSMA part CD protocol. Have any doubts so far? I'll stop here and I'll continue the next class in my regular class at 11 itself. I have class at 11. I'll come.